Yeah. So, I think some of you might still not have completely gone through run over the derivation that we did yesterday. So, let me quickly summarize once again. Okay. So, the important thing when you talk about nanoscale energy transport is to first understand whether you have a transport parallel or perpendicular if you consider a particular nanostructure. Okay. So, depending on that, so you have to formulate the Boltzmann transport equation, and for the case of electron transport which contributes to current flow. So, that is the example I have considered, and I have also taken a case of transport of electrons along the x direction, and the confinement of the film is along the perpendicular direction. So, for such a case we have written down the Boltzmann transport equation, which is of this particular form. Okay. And what is important here is to find out the perturbation function g and its variation with respect to y. Okay. So, this is what is going to result in the size effects. So, therefore, now we have a ordinary differential equation which we could solve, and then we could get a solution in terms of y and s naught of x, right, where s naught of x for the case of electron charge transport is given by this particular expression. Now, after this point is now coming to the solution. So, we have two contributions to this perturbation function or any non-equilibrium distribution function, because this non-equilibrium distribution function is now going to have a directional dependence. Okay. So, therefore, it is going to vary with theta even in case of one dimensions. So, it will have a variation with respect to the direction cosine cos theta. So, in this case we have to split up the distribution function into two components, one which is going in the positive y direction, the other going in the negative y. So, we have identified those two components, so that we can apply the two boundary conditions at y equal to 0 and y equal to d and find out the constants. Okay. So, accordingly we determine the complete solution, and so this is what you get, g plus and g minus. Okay. So, once you get the distribution function, so all that is required now is to put this in the expression for the charge flux or the current flux. Okay. So, therefore, in terms of f, if you write, so basically we know that f is equal to g plus f equilibrium, and then if you integrate f equilibrium over the solid angle, it is going to be 0, because it is uniform, not varying around about the solid angle, and integral cos theta sin theta d theta will be 0. Okay. So, therefore, all we are having is we end up with an expression only in terms of g plus and g minus. So, we have split the polar angle or from 0 to pi by 2 and pi by 2 to pi. So, we have written that in terms of the direction cosines. So, correspondingly -1 to 0, 0 to 1, and then in the expression for g, we already have this v tau mu. So, in the case of negative direction cosines -1 to 0, we can write this basically as so value of mu here is going to be negative, and we can replace this from 0 to 1, and the corresponding value of mu will take negative values, whereas if you look at the other side, it is going to be positive. Okay. So, that is how we have rewritten this in terms of mu and replaced the limits from 0 to 1 instead of -1 to 0. And then after this is simply integration, so we use all the rules of integration, and finally we write the term on the left hand side such a way that we have current flux divided by the electric field plus whatever electrochemical gradient. Okay. So, this is equivalent to basically your electrical conductivity, right. And on the right hand side we have basically a more complex expression, out of which we can identify this group of terms here, which is circled, basically is nothing but similar to your bulk electrical conductivity. Okay. And one more thing I just forgot yesterday is that this is a flux, correct. So, that means if you are talking about transport between two plates, you are talking about at some point you are evaluating this quantity. Okay. So, similarly if you want to calculate the total flow, okay, just like heat flux and heat flow. So, you have current flux and current flow, you have to integrate this over this entire length from 0 to d. So, therefore, we have to also do one more integration here from 0 to d dy. Okay. So, because we also have a variable y here, okay, in the solution for g is a function of y. Therefore, to also when you finally get the solution, we want a net quantity. Okay, we do not want electrical conductivity which is varying with y, that does not make much sense, although I mean it is a flux and also it is a function of y, but finally when you are talking about thermal conductivity, electrical conductivity, they are for the entire system. So, therefore, what we need to do is integrate this expression across that particular plane from 0 to d dy, and however we are dealing with on the left hand side terms of flux. So, the right hand side now it is in terms of the integral value. So, therefore, we have to divide by d in order to still make it a flux unit. Okay. So, that is the only thing I think I missed yesterday, and if you do this integral with respect to y and also with respect to mu, we have two integrals, double integral. Okay, we have terms 1 minus mu square exponential minus y by v tau can be replaced with the mean free path times mu. So, therefore, this entire expression is a function of variables mu and y, you have to integrate them, and if you integrate, so you can with respect to y, if you first integrate, okay, so all the y's will be replaced with d. Okay. So, then you will be simply having a non dimensional parameter d by lambda, which is So, this is your zeta, which is your 1 over Knudsen number, right. So, inverse of your Knudsen number. Apart from that, you have to now integrate with respect to mu. So, that integrals I have expressed in terms of the integral functions E3 and E5. Okay. So, you have two terms here. So, one, if you multiply this quantity with this, you have one parameter mu times exponential of this, right. So, when you first integrate with respect to y, you get this mu parameter, and then next other parameter will be, there will be mu cube times this. So, there are two integral functions. Okay. So, that is why I denote them as E3 and E5. So, where you can evaluate the corresponding E3 and E5 integrals using this expression. So, basically we finally reach this point, which gives you the ratio of electrical conductivity for any nanoscale film as a function of your bulk electrical conductivity. So, what it means is, if your Knudsen number is very small, your zeta value goes to infinity, and this term minus that second term will disappear, and therefore, it will reach the bulk value. And for larger values of Knudsen number, your electrical conductivity is reduced, right. So, same way, if you work out an expression for the thermal conductivity, whether it is thermal conductivity of only electrons or you take case of phonons, you will also get a similar expression similar to the ratio sigma by sigma b, you will get k by kb which is similar to that. Okay. So, I think this is what we have seen. So, I mean all you have to do is you have to go home and make sure you work out again and the steps, intermediate steps. So, then you become more comfortable with the derivation. That is, it is not difficult. Okay. So, we have already done most of this before. So, only that you have to be careful with the integration.
Sir, I did that, and that negative sign is only that goes with that when we take that ratio, otherwise that negative sign will be continued till that end of that integration.
You are talking about the mu?
No,
Negative in the
that minus 1 upon 4 pi, and then, then these two terms, j and j, minus 1 upon 4 pi and then 1 upon 4 pi. That minus term is comes to up to the last integration, and when we that divide with that sigma b, that bulk,
okay.
then that negative sign also will be.
Okay, you are saying that the sigma b is having a negative sign, is it?
Integration of something.
Minus e square, is it? So, what do we have here? Do we have a minus
so
e square?
Negative sign will be cancelled.
Oh, okay, okay. So, in that case we have to retain, you may be right, because I think we have a negative sign here, because this 0 to 1 is basically absorbed here.
Yeah.
Okay, so already we put a negative sign. So, therefore, there is no reason that this should simply disappear. Yeah. So, you may be right. So, this will continue till here, and correct. So, we can just say that, and this is your, including your negative sign, this is your sigma b, right. Yeah, I think you can be, but at least it is okay. I mean, if you are not careful with the signs, and negative sign, on for the entire term, then it is okay, but inside the within the terms you have subterms. So, if you make mistakes, then you will have wrong expression. Yeah, 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 because these are all very lengthy expressions. So, it is very difficult to keep track of all the signs one after the other. Okay, possibly one of the lengthiest expression in this course. Okay, right. So, this is the case for transport parallel to the films, and also with a diffuse boundary condition, diffuse scattering at the boundaries. What happens when you have specular scattering at the boundaries? Okay. The solution, general solution in terms of C1 and C2 is still going to remain the same, that is not going to change, only now we have to apply the specular boundary conditions to determine the constants. Okay. Therefore, your G plus will be C1, still the same expressions that we had written down, minus S naught. G minus will be C2 minus S naught. Okay. So, this is for the case where mu is greater than 0, this is for the case where mu is less than 0, this direction cosine positive and this is downward direction. Now, all that we have to do is what specify the boundary condition for specular scattering. So, at y equal to 0, if you are talking about a specular surface, so you have an electron or phonon which is coming in a particular direction theta, and it is going to scatter with the same angle the other direction. Okay. So, similarly on the top boundary also. So, incident and reflected angles are the same. Okay. So, therefore, at y equal to 0, you are, if you call this as f plus, right, that is the distribution which is scattered going in the positive mu, and this is your f plus or f minus. This is coming into the boundary, f minus. This is coming with a negative direction cosine into the boundary, and that gets scattered and it is coming out in the positive direction. So, therefore, at y equal to 0, what is unknown is f plus, because that is what is coming out of the boundary. So, therefore, in this case f plus at y equal to 0 comma mu will be equal to f minus at y equal to 0 comma minus mu, right. So, whatever distribution function is incoming is just reflected without altering the value of that distribution, but only the direction is changed, in the sense that it is a mirror image of this. Okay. So, it is coming in the negative mu, and now this is going in the positive mu, but with the same angle, with the same direction cosine and same magnitude. This is like a mirror image. Okay. Similarly, at y equal to d. So, at y equal to d, what is need to be determined, f plus or f minus? This one, what is coming out of the boundary, f minus, okay, and what is reflected, f plus. So, therefore, f minus at y equal to d comma minus mu is equal to f plus y equal to d comma mu, correct. Okay. So, also this means since f equilibrium is independent of direction, the same thing can be said about g plus. So, g plus at y equal to 0 is equal to g minus at y equal to 0, and similarly g minus at y equal to d is equal to g plus at y equal to d. So, therefore, you please use these two conditions into these expressions, determine the constants C1 and C2. Yeah, just I have given that, but you do not have to. So, as long as you know that f minus corresponds to negative mu, you do not have to put a negative sign. Yeah. Okay, so you please substitute this, find out the constants. What do you get? Okay, so from first condition y equal to 0, right. So, you get C1 equal to C2, but still that does not tell what is the value of C1. So, then you have to apply the second condition, y equal to D. So, that is telling you C1 exponential minus d by tau v mu minus S naught is equal to C1 exponential minus d by tau v mu minus S naught. So, S naught cancels. Even this also will cancel? Yeah, because here you have to be careful. This mu is negative. Okay. So, if you want to properly write it, you can put magnitude of mu, and this is negative. If you put magnitude of mu, then this will be positive. Okay, that is maybe a clearer way of explicit way of writing. Now, what we are saying, now this expression left hand side should be equal to the right hand side, but clearly how can this be possible? You have one side positive mu, other side negative mu. So, this can be equal only if C1 equal to 0, right. So, therefore, C1 equal to C2 equal to 0. So, then therefore, what happens to G plus and G minus? They become same, right. So, G plus equal to G minus will be equal to minus S naught. So, now you go back to the expression for charge flux and substitute this and see what happens.
Y is equal to d, G minus should not have an exponential thing. Because it has a d minus y function exponential.
No, the d minus y function comes from the diffuse boundary condition, correct. For the specular case, now we are starting from again the general solution. The d minus y comes because in the diffuse boundary condition your constant turns out to be exponential d by tau v nu. Okay, your f is equal to f equilibrium. Okay, please go back and see what we have done yesterday. Okay, this is the condition we gave for diffuse. So, the constant C2 turns out to be that. Okay. So, you can complete that exercise. I will only give you the final result. So, this will simply come out to be this. Hmm? Correct. Both are same. Okay. So, therefore, the other additional terms, that 1 by 3 minus sigma d, that will actually not come, right. So, all these integral functions with respect to mu and all will not be there. So, only you have the sigma b term on the right hand side. Okay. So, it very simply turns out to be the same as your bulk electrical conductivity. Okay. So, this is a completely different expression. Just if you change the boundary condition, you see that there is no modification in your electrical conductivity for this case. Okay. So, therefore, the nature of the boundary condition tells you whether there will be a destruction in momentum or not. In the case of specular boundary condition, you are perfectly conserving the momentum. Okay. So, whatever is incoming distribution is the same as outgoing. Okay. There is no loss of momentum, and therefore, there is no need for reduction in the conductivity or electrical or thermal. Okay. Whereas, in the case of diffuse scattering, there is an associated reduction in the energy of the emitted phonon or electron due to this distribution over the entire azimuthal or polar angles. So, that will result in the consequent reduction in the conductivities. Okay. So, therefore, it is very important to understand that you cannot simply say electron transport parallel to film is always resulting in reduction. It depends on the kind of boundary scattering that you are applying. Okay. Most of the real time surfaces are neither entirely diffuse or entirely specular. So, they will be somewhat in between. So, therefore, how do we categorize that? We use what is called as a specularity parameter. Specularity parameter. So, this is given by notation P, and if this is equal to 1, it indicates it is a purely specular scattering. If it is equal to 0, it is completely diffuse. Most of the real surfaces have between 0 and 1. We do not know exactly, but it can vary from 0 to 1. Okay, and depending on whether you have a specular or diffuse parameters, we have independently got the expressions. Now, what happens when you have somewhere between 0 and 1? So, in that case, the expression turns out to be, including this specularity parameter also, okay. So, you have the specularity parameter P appearing in these cases. Okay. When you put, for example, P equal to 1, this entire term disappears and you get your other expression. If P equal to 0, you get back your diffuse scattering expression. Okay. So, this is also a very generic case for different values of specularity parameters. Okay. Yeah, that is the, yeah. So, this is the integral, so 0 to 1, the entire expression times d mu. You have to integrate it. I have not explicitly written the integral functions now. Okay. So, as E3, E5, I have just given the total expression. So, the last part that I want to, I do not want to derive this because this is somewhat more clumsier than the transport parallel to the film and might confuse you. So, what I will do is, the case where transport is perpendicular to the film, I will only give you the final expression and anyway since you are going to do this programming assignment, so you will be doing the programming assignment for the transport perpendicular to the film. You can also do parallel to the film and compare with this expression. Okay, you can give either diffuse or specular and you can verify whether you are getting similar to this analytical solution. But mainly the more challenging case is the transport perpendicular to the film. Okay. So, you will solve the Boltzmann transport equation, find the numerical solution, and I will only give you the analytical solution with which you can compare your results. So, therefore, for the case where you have transport perpendicular to the thin film, okay. So, if you go back and revisit what we have derived, the Boltzmann transport equation for the transport perpendicular to the film. So, this is the expression, correct. So, we have both F equilibrium as well as G, both of them in the direction where the transport is. Okay. So, now if you solve this, I will give you the final expression. Okay. I will write the final expression in terms of the intensity. For example, right now what I will do is I will only give you the expression for phonon transport, because that is what you are going to do in the numerical solution also, phonon transport, and I am going to express this distribution function in terms of intensities. Okay. So, I have also uploaded the reference paper on Moodle, okay, so which gives you the equation cast in terms of the intensity of phonon transport. Okay. So, you will be solving in terms of, rather than distribution function intensity, it is just a small modification, nothing more. So, therefore, because why intensity is much easier is you can directly get the expression for temperature from intensity, similar to your radiation. So, in radiation also you define the total intensity from which you directly extract your temperature. So, the similar way when you are talking about phonon transport also, we are interested in finally plotting the temperature distribution. So, if you are calculating the distribution function, so then you have to convert that in terms of equivalent temperatures and then get the, that also can be possible. But more elegant way is to write directly the Boltzmann transport in terms of intensity, and therefore your temperature can be directly extracted. So, in terms of intensity, the solution, this is your equilibrium intensity here. In place of F, I am just writing in terms of I, 0 mu, and again these are integral functions, the same integral functions what I have given for the parallel case should apply here also. So, this is I plus at y equal to 0. Okay. So, basically the boundary condition what you are applying at y equal to 0 is this particular intensity, and at y equal to d, that is your boundary condition I minus, okay, the intensity of the phonon which is coming out at y equal to d in the downward direction. Okay. So, this plus, so you have 3 terms essentially, 0 to zeta I equilibrium E1 eta prime minus eta d eta prime. Eta prime is a dummy variable, okay, where now I equilibrium is related to your temperature like this, okay, and your integral functions x power mu power mu power n minus 2 exponential of minus x by mu d mu, the same integral function. So, these are popularly called as Fredholm integral functions. Okay. So, all you have to do is calculate the temperature distribution as a function of eta. So, eta is nothing but your non-dimensional y. So, I am defining eta as y by the mean free path, and zeta is nothing but inverse of your Knudsen number. Okay. So, this expression, if you plug in, solve it in MATLAB or even Excel sheet, this will give you the temperature as a function of y or non-dimensional eta, from eta 0 to whatever values. Okay. So, therefore, this is the expression. Now, if you plot it, how the temperature distribution looks. So, I would like to define a non-dimensional intensity. I will call this as I equilibrium star, which is a kind of a non-dimensional temperature, because we have related the equilibrium intensity with temperature, right. So, it is similar to plotting your non-dimensional temperature, right. So, this is defined as I equilibrium eta, that is basically this expression as a function of eta minus, this is your boundary condition at y equal to d, right, and the boundary condition at y equal to 0 minus the boundary condition of intensity at y equal to d. So, I am basically non-dimensionalizing my local temperature with the boundary temperatures. So, this value of I plus and I minus can be calculated from the corresponding boundary temperatures. So, if I fix my bottom boundary temperature at T1 and T2, I can use this expression, calculate for T1 what is the value of I equilibrium at the bottom wall, and similarly for T2 what is I equilibrium at top wall, and therefore, whatever is coming out should come out with that particular intensity, right. Okay. So, that is dictated by the boundary conditions or temperature boundary conditions at the top and bottom. So, if I normalize and plot, so the normalized temperature versus eta, so that is the local variation of temperature with position. So, this value will be between 0 and 1, right, it cannot exceed the boundary values. At Knudsen number of 0.1, what will you expect? This is similar to your Fourier's law, a linear variation in temperature from one end to the other. Now, as your Knudsen number keeps increasing, this could be Knudsen number of 1. Suppose you go put a very high Knudsen number of 100 for example. Okay. So, in that case you get a perfectly flat line. So, what does this indicate? So, there are no scattering between phonons. So, for very large Knudsen numbers approaching infinity, this is called ballistic transport. right. So, hardly the phonons see each other. So, they directly the phonon from this boundary will come and hit this boundary. So, this is at temperature T1, this is at T2. So, it will come with an intensity corresponding to that temperature and directly land on the second surface. But what happens, there is a shock, because the second surface is at temperature T2 and this phonon does not know that. Okay. So, therefore, there will be a discontinuity at the boundaries. So, this is your boundary, right, these are your boundaries. So, this phonon will see a shock here, and similarly the phonon which is going from this to this. So, it is having a temperature T2 here, it lands on this boundary, but it finds that the temperature is T1, but it cannot now adjust, already it is gone and it is stuck there. So, therefore, you find there is a jump. Okay. So, this kind of discontinuities at the boundary or temperature jumps are a characteristic of this nanoscale transport. At macro scale you will never have that, because the phonon collisions are sufficiently so much so that they can transfer all the information from one end to the other. But in the nanoscale subcontinuum regime, this transfer is not possible, because you do not have complete information communication between energy carriers. So, you end up with all this discontinuity. Or in other words, if you look at y equal to 0, there your I equilibrium will not be same as what is the emitted phonon intensity. Understand? So, the emitted phonon intensity will be different from the corresponding equilibrium value. The corresponding equilibrium value, equilibrium means it is an average or summation of the phonon intensity in all the directions. So, what is coming out will definitely be different from what is coming in. Okay. So, therefore, your I plus will not be same as I equilibrium. And what is I equilibrium? That is the indicator of temperature. Temperature now how do we define in nanoscale? Okay. There is no, it is not a physical equilibrium thermodynamic temperature in nanoscale. So, temperature here is only an indicator of the local energy. Okay. So, local energy density, you have to somehow express this, and therefore, we call this as temperature. But unfortunately, this becomes the same value as the physical temperature in macro scale. Okay. So, therefore, it is more appropriate to refer this in terms of intensities or energies rather than in terms of temperature. Okay. And similarly, so at y equal to d, your I equilibrium is not the same as your I minus. Okay. If this was there, then what will happen? This is the case where your Knudsen number is less than 0.1, then this will be equivalent to your Fourier's law. So, everything is at local equilibrium. So, therefore, there is no temperature jump. But for the case where Knudsen number is greater than this, Knudsen number greater than 0.1, you are talking about say 10 or 100 or 1. So, in all these cases this is not satisfied. Okay. So, this is a very important characteristic. So, people also refer to this as temperature slip. Okay, this kind of temperature discontinuity is temperature slip. Right. So, this is the characteristic of transport perpendicular to the film. So, I think we will stop our discussion on nanoscale energy transport with this, because more or less now you have enough idea what is happening even in one dimension. So, so the basic the key understanding is that all the size effects are becoming very important at higher Knudsen numbers. So, when we talk about now temperature distribution, this is basically temperature slip, correspondingly your thermal conductivity also will start reducing because of this. So, these are additional resistances at the boundaries. So, therefore, effectively your nanoscale thermal conductivity will be lower, and this keeps dropping with increasing Knudsen numbers. Okay. So, from tomorrow's class we will start looking at micro scale transport. The micro scale will appear much easier now that we have done the nanoscale, because you have the proper foundations. So, it will, and also the equations are more familiar to you. So, most of them are continuum equations. Okay. So, I hope that most of you were able to follow at least 70 or 80% of this content. Sometimes it might been completely new altogether, new topic, and we have, it is also quite intensive in mathematically, but nevertheless it will give you a new perspective about this kind of transport. Okay.